Okay, well, first of all, I would like to thank the organizers for allowing me to be here. It's a pleasure. Oh, hang on. I'm talking to, right. No. Yes. Okay. So the talk is about what I really want to talk about, something called tunneling time. But to do so, I would have also to talk about something called weak measurements. And this is one of the topics of the conference, so I think it should fit. Let me start with the tunneling time. If I press the right button, yeah. So the tunneling time problem. There are different ways to look at tunneling. Well, first of all, you can tunnel at fixed energy. You have plane waves coming in, going through, reflected. You can have wave packets going in, partly reflected, partly going through. And, well, if you think about it for a second, you think, well, something going in, there must be some time parameter which tells you how long it takes to get through the barrier. And if you think a second longer, you discover that the textbook on quantum mechanics doesn't tell you what that parameter is. And so the search for it in controversy continues, and particularly the interest in this subject became, again, resurfaced because of the attosecond ionization. Basically what these people do, they have an electron sitting in an atom, and there's a potential which looks like a step. And then they flip it and turn the step into a barrier, so letting electron escape, so the bit of it escapes, and they flip it right back on, and they do it extremely quickly. It's attosecond. Just I always forget what it is, but actually it's 10 to minus 18. I checked this morning, so very few seconds here. So why they do it? Well, they hope to flip it, quick enough, then the electrons would not have times. If there is a time which characterizes tunneling, the electron wouldn't have time to escape. If you open the door, it takes 1 second to open the door and close it, and it takes 2 seconds to go through the door, and nothing will go through if you open for just a second only. Now, the problem is that there are some people who think, who claim, and there are a lot of people here, and they claim that this tunnel time is finite. It takes finite time to tunnel. And some people say, no, it's zero time. And there are so many people because they make experiments, and they also make good calculations. So what I want to talk about is really, well, before saying that something is zero or non-zero, should we not be trying to find out what the time, sorry, what's it? Okay, what that parameter, whether it exists. That's complete disaster. Sorry. Right, back here, back on. Right, so now I have to go back to the first half of my title, to weak measurements. And what best way to introduce something is to give some publicity. So that's what Mail Online says. If you see, scientists finally separated neutron from its spin. So the neutron was a thing which sort of here, and was rotating, and they made this neutron go there, and its rotation go the other way. So neutron from its magnetic moment for the first time, you see. So it's something to talk about. So we want to talk first about the weak measurements which are involved in this sort of scheme. So the first thing is I'll go to the basics. And what better place to go to the basics than to Feynman's lecture on quantum mechanics. Feynman defined quantum motion the following way. He says, outcomes of your experiments are random. They are only probabilities. To find the probability for something, you have to take a complex number, which we call the amplitude, square the modulus, and get the probability. He also says if you get the same result by two different ways, then, and you can't distinguish between the ways, then you add the amplitudes, square the modulus. If on the other one, you can't distinguish between the ways, or somebody you can in principle distinguish, well, you do the opposite. You square the amplitudes and add them and get the probability. And of course, we all know that, and we really won't go anywhere beyond this, whichever page it is of Feynman's course. Right, so what does Feynman say? Well, in quantum mechanics, if something happens, you have an amplitude for it. If something A happens, you have an amplitude for A. If happens A, then B, then you have an amplitude for A, then B. Sometimes I put an arrow here, sometimes I put just a dash. So, right, if you have three things, A, then B, then C, then you have an amplitude for going A to C, to B, then to C. And what's important is that if you have an experiment like this, you have an amplitude for the whole thing, A, B to C, the amplitude for this whole sequence. And by the way, if you prepare the system in A, and only look at outcomes in C, then you say you pre-select in A and post-select in C. Very good. So the amplitude for the whole sequence, I would like you to remember because I'll show you in a minute why it's important. Right, what's the simplest way of doing this? Well, quantum system, two-level quantum system, it pre-selects in the state psi, whichever you choose. Now, it's post-selected in phi, whichever you can choose. It can go there if there's a basis B1 and B2. It can go there first psi, then B1, and then phi, or first psi, then B2, and then phi. If we don't do anything to this system, we can't tell which way it goes. It's the first case. So you take these amplitudes, which are of course trivial, start with psi, then evolve to until time t2 when it's supposed to go through B1, then B1 next to phi, right? And so two amplitudes, two pathways, and one pathway, two virtual pathways. And this is, of course, nothing more than a two-slit experiment in a nutshell, right? Okay. But suppose we want to know, suppose we want to check how it gets there. In this previous slide, you don't know. So what you do, you measure your state here. You make a von Neumann measurement. Well, what's a von Neumann measurement? Well, it doesn't really matter. What matters is that my pointer, well, is a point particle. Well, the point lives in one dimension. Initially, it has a wave function shape, which was a Gaussian, say like this, and it sits around 0 with certain width. Now, when I finish my experiment and post-select in phi, I will have this wave function entangled, first entangled with the system, and then purified again after post-selection in phi. So we'll have a final state of the meter in coordinate representation, and this will be the initial Gaussian, initial shape shifted by B1, where B1 is the first eigenvalue of that operator I measured, and the same shifted by B2. But what I want to show, what I think is important here, is you see that what hooks with the meter is precisely this amplitude for going psi, then B1, then 2. So whatever you do from this point on with this meter, you'll learn something about this amplitude. This is what the system contributes to your experiment. Very well then. Okay, so everything now depends on how broad or how narrow your Gaussian, your state of the meter is. If it's narrow, so you see narrow in a sense is much narrower than the distance between the B1 and B2, then when you do, you have a strong measurement, accurate measurement. So each time you'll find the system either going through B1 or going from B2. So now with this additional equipment, you can tell which way you go. So Feynman says, add the probabilities. So square the amplitude individually and add the probabilities. So great. Well, just two-slit experiment. Now you know which way you go, but you lost the transition. The probability to arrive in phi, you see, is no longer this, but this. So you destroyed your transition. This is not what you want to do. If you're talking about tunneling is what happens only rarely. And if you do this, and this, I don't think when you suddenly go over the barrier, you destroyed the transition you tried to study. Well, tough. But we knew that already. But suppose we want to know which way question without perturbing. We also know it's not a very good idea. Why? Well, because you're up against the uncertainty principle here. In a sense, Feynman's third statement said if you can't determine which way you go, then add the amplitudes. Then converse is if you add the amplitude, you can't determine which way you go. And you can't determine some very profound sense, some very deep sense. And I want to dwell on it just a little bit longer and give you an example of purely, forget quantum mechanics, something purely classical, a classical question which doesn't have an answer. Well, here I have just the desktop, and I have 2 drops of oil. Sorry. So I have 2 drops of water on it, and I put a grain of sand in one of them. And I ask you, somebody asked me, which of the 2 drops is my grain of sand black thing in? I said, oh, sure, it's in the first one. Well, this is a little tilted, so that's usually my water drops go closer to each other. And here's still in the first one. But when they coalesce, and someone comes and asks me, which of the 2 drops it is now? And I say, well, sorry, it's a silly question. This has no answer. But this is not a very nice person talking to me. He has a gun. He puts a gun to my hand and says, tell me. So I say, okay, I don't care. It's number, I think it's in the water drop number 100. And he said, all right, well, I'm happy, let's go. So what I'm trying to say here is if a silly question which has no answer can have an answer in the form of anything at all. And this should prepare us to see what happens if you try to do the, which way without destroying interference. Because the only way, if you remember the previous formula, there was a G sitting here, and the G sitting here. The only way to preserve the coherence is to make G so broad, so wide, and the measurement that I can put it outside, and then these 2 amplitudes continue to interfere unimpeded. And by the way, there's got to be an A here, but it doesn't matter. And so I get right. But if I make my initial state of the point extremely broad, in my picture it's almost constant here. It goes a long way that way, long way that way. And if I make my experiment, then my meter will tell me, well, anything at all with almost equal probability. So you see, my poor meter can't tell me. Sorry, you're asking a silly question. It's only there's no way. It can't talk to me. It's only way to answer this question is to give anything at all answer. Right, again, that's not surprising, but someone may come to me and say, so that's fine. That, if you can't tell which way and try to measure it without destroying interference, you get any answer. But, okay, well, let's do something else. Well, however broad your state is, let's calculate the average position of the meter. And that thing cannot be arbitrary. It will be a fixed number. So if you do a million of these measurements and in the end work out what this F is, well, you have a number. And that number will tell me something. So how does this sit with, yeah, okay, I say fine. So we go and do this measurement, this calculation. We find that this average thing comes to real part of a complex number where my eigenvalues of my operator are multiplied not by probabilities, but the amplitude. So the amplitudes are not my original amplitudes, but normalized to 1. They call them relative amplitudes. They are renormalized in such a way that we add them all over all possible things. You get 1. So that's my answer. Okay, yeah, very good. I made my average thing, average, and I find some number. And someone like Lev Weidman, who would here said, "Oh, this is an element of reality because you get it. You will get it every time you make a million of these measurements." So have we? Right. Okay. 2 things. First of all, you get some statement about this amplitude, as I promised. Should we be surprised? There are people here who could be surprised and say, "Well, the amplitudes are something just computational tools they are in our heads. I don't know where. You don't really need them. They're not physical." No, not quite so. I mean, you take any perturbation theory, you get the same result. For example, you see, you have a much simpler experiment in which one outcome is A. The probability of A is the amplitude mod squared. You measure you change the amplitude a little, experiment a little bit, so it's now the old plus small variation of the amplitude. Change find the probabilities, find the difference, lo and behold, you find something about the amplitude, the real part of this product. Is it strange? Not at all. I mean, whenever your theory is built on the amplitude, you study in perturbation limit response of this system, we all know something about the amplitude. So that shouldn't be surprising. Right, but what about the uncertainty principle? I told you I can't learn anything about this system, and it seems I have through the, not through the individual position of the pointer, but through average position of the pointer. So have we bitten the uncertainty? Not really, because you see, if I go over all my initial and final state, I can make this value I just showed you be anything at all. Well, anything at all. Real, positive, negative, equal to the what you get in the measurement. It turns out you can prove this. So in the end, if you not make just one experiment with one pre-post selection, but all possible post selections, you get any value at all. You wouldn't be able to tell whether you're experimenting with 2-level system, 3-level system, 4-level system, or anything at all. So the uncertainty principle is back and forth. And you just have to look one a little bit further, and then you see that uncertainty principle smears everything you may want to know. Now, so that would be it. Right. Okay. This problem has a discussion of these things. I believe started on the wrong foot. So it started by Aharonov and co-workers, and I don't know. I said what mine came to work was Aharonov's folly. But then I thought, well, that's rude. So I just put here, and you decide what it was. So it started with a paper in 1988, which said how can spin on half particle result be 100? It continues to 2015 when these people still continued explaining us what quantum weak values are. So it's a big mushrooming, booming, blooming topic, and I want to talk about it very briefly. So what did Aharonov and co-workers do? Well, they did precisely what we did before, except they put a spin, they put some intermediate states, they ensure that the amplitude are this and this, and then lo and behold, this weak value. So now I call this sum of a weak value is 100. That's their result. So what have they found? Well, I would say they found the fact that in this system, if you take the first amplitude multiplied by 1/2, and add to it, take the other amplitude multiplied by minus 1/2, add them together, you get the result 100, which is of course correct. What is incorrect? Well, incorrect, I think there are many things incorrect here. Well, first of all, they say okay, we got new physics out of it. No, I disagree. They get something about the amplitudes where they put there in the first place. Right. The claimed result was obtained by usual measuring procedure. Not true. It's precisely where uncertainty principle should forbid you to do anything meaningful. And finally, they thought the result was unusual. Look, 100 is very unusual, but not true. It would be unusual if they couldn't get 100 minus 100 or even this number I don't know how to pronounce. They could get anything. That's uncertainty principle ensures it's normal to get anything you want. It's not surprising to get 100. And from this came all sorts of things. You see, surreal element of quantum mechanics, negative kinetic energy, weird quantum phenomenon known as Cheshire cat, electron with disassembled charge, and also strange paths of photons which don't have continuous trajectories, and people will be talking about it tomorrow, and so on. Great. So why did they do? I mean, well, your guess is as good as mine. Well, first of all, they wrote everything a different way. They wrote the same form as I've given you before, except it hides the amplitudes, which I think are essential for this. It looks conspicuously like the usual expression for the mean value of an operator in the state psi. And they say, look, we extended this to that, and they called it ABL. Well, it doesn't matter. So does this look convincing to me? No. The other reason maybe because they did something else. I think I just tried to make initial state of the emitter broad, and they tried to make the coupling with the emitter small. And it's the same thing because of course you can keep and reduce the coupling, or you can keep the coupling what it is and reduce for this particular von Neumann meter the width. It's one and the same, but except when you reduce the coupling, anything just goes into a point. It's very hard to see what happening there. So maybe they thought, something's happening there. Cool. All right. Okay. So this is my nasty slide to this. So my argument is what weak measurements were planning to do. They start with amplitude and interference as we know them. Then they invented something called the weak measurements, and they say what will lead to new physics, but it tells something new about quantum mechanics. The trouble is they don't. You see, they start with amplitude and interference, they go do the weak measurements, and they go back to amplitude. So I mean, what the argument, the discussion could be like, what can be said about the system with interference present? So, well, Feynman said they are amplitude, and what we make the measurement, and what are these amplitudes through weak? Well, they are amplitudes. Uncertainty principle. You can't really beat uncertainty principle. Don't do it. Right. Okay. Well, it doesn't have to be apparatus. It can be, it can be any function on a path. Well, the paths can be Feynman paths. Here they are, and instead of measuring operator at a given time, we can measure something which pertains to the whole of the path. Right, and then I get the weak value of the functional, which looks exactly the same, except the real part, except with the sum over paths, so this continuous integration. Right, so here's my how much? 5 minutes. Oh, good. Oh, bad. Right. So you either measure. Well, that's your dilemma. You either measure accurately and get and then the mean position of a pointer is a statement about the probabilities. Or you measure weakly, you keep your transition, but your meter skims over the amplitude, and you get the statement about relative amplitude involved in the transition. So back to tunneling time. Now, in this slide I need to show you. Before discussing tunneling time, just imagine well, you can measure in two possible ways. There's a classical particle going from here to here. It's semi-classical, so the interference, it goes through path and reflecting here and come back. There are two classical paths to interfere. This red path spends 3 seconds in the region I'm asking. The other one spends 1 second. So the 3 seconds, 1 second, and then they interfere at the end. So in one hand, you just feel it. You can hold, in one hand you hold 1 second, the other hand 2 seconds, and the whole motion in 3 seconds. And now try to say how much time on the whole. You can't. Is it once? No. Is it 2 seconds? No. Is it? No. It's indeterminate. We've just been with this, through this before. And if you do it, you measure something called Larmor clock, which spins in magnetic field. I can tell you. So you do it, and depending on what you do with the Larmor clock, well, first of all, there is a just very quickly. There's a particular function, or this one, on the Feynman pair. It calculates exactly the net time a Feynman pair spends in the region. Now this you can measure. This you can measure with the Larmor clock. And if you measure it gently, you know what will come out. You will get the weak value of this tau functional, well, just in the form before. And it turns out if you do something to the Larmor clock, depending on what you do to the Larmor clock, you can measure real part of this, you can measure imaginary part of this, and you can measure modules of this. And then you probably say all these options, and Büttiker did many years ago, and say, well, I think I like this modulus. That's the right answer. Oh, why? Well, it's real. It's always positive. Well, no complex time. No negative time. None of this nonsense. It's positive and real. There's just one slight problem here. You see, in the transition I showed you, if I find this amplitude, the modulus of this weak value turns out to be 1.4 hours, but only 3 seconds were available for the system to move. And that's a bit strange. I mean, it seems to have more. Well, you can almost see the things in Nature and Mail Online. Well, scientists have made particles spend more time than it has, and they probably say, important application of holiday makers, prisoners spending time, and possibly the financial markets, because they always spend more than they have. What they should be saying, I think, the two amplitude, well, something much less but exciting, but I believe correct. The two amplitudes are such that if you multiply one by one, the other by 2, add them up together and divide by their sum, you get the number 499, and you can measure it. You can have this number. So don't do that. Do this. Now it gets worse. It gets worse. It gets different. Now see, Now there's a complex quantity, and there are various ways of measuring its real part or imaginary part. And there's different transition. You see there, my weak value of time functional is real part is 0, and the imaginary part happens to be 5. Well, and there's our usual Bob and Alice, and they do each does her own thing. So Bob, Alice rather, has a lab which measures real part of this thing, and Bob has a different thing, a different machine which measures real part. And then Bob reports in Nature, it takes no time, 0, I measured, there's no time. Alice, Bob says, no, it's 5 seconds. And they continue arguing with each other, and this argument has no resolution because they're both right. Bob did measure 0, sorry, Alice 0, Bob did measure 5. But they're wrong. They're talking about things which doesn't exist, which represented by this complex. And this argument can go on forever, in nature, wherever. It has no resolution. No. Right, I think it probably stop here. Just one quick mention, just very, very quick, 2 minutes. So if you do it in the case of tunneling, you get something complex time, which we did many years ago. It's essentially a derivative of transmission amplitude, of log transmission amplitude to the potential. But you say, God, that's all nonsense, where we don't believe in Feynman paths, but we can do something which wouldn't fail us, or would it? I will look how far. Well, it's a classical experiment. I shoot free particle, I shoot a particle over the barrier. The particle of the barrier lies behind some distance behind. And calculating this distance, I can calculate, or measuring this distance, I can calculate the excess time the particle which lags behind has spent in the barrier. Now, if I do this in the quantum case, I get the answer. Well, we're replacing the particle position by the mean particle position. The only trouble, you see, it will look by time derivative of this time derivative of log with respect to the momentum, to the other. So why should we trust it any more than the previous results? And we shouldn't. And if I had time, I would play this game. So the game is called Spot the Weak Measurement in all this experiment. But I don't have time for that. So I go straight to conclude. Oh, right. So just okay. This time turns out to be too short now. If you do it like this with wave pack, it looks like the wave packet spent 0 time there, and there were people used to nymphs who said, relativity and quantum mechanics don't live together very well, and so it's 0 time. Tunneling takes 0 time. We can violate Einstein causality and blah 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 blah. And but of course you can, and if you believe what I said before, then what we just get is just a statement about certain amplitudes, which when you add them up in a particular way, you get a particular answer. So Einstein causality is safe, I'm happy to say. And thank you very much. Yeah, okay. Conclusion. Any interfering path of a pathway is always some relative amplitude. If you keep interference intact, you get the statement about amplitude like this. It scrambles the which way question as it should. As it required by uncertainty principle. It gives you answers such you cannot tell. You cannot tell which way it was taken. And this is precisely what happens with the times when you try to reconstruct classical Simon quantum scattering. They are lost to interference. I think this is the key word in all this. The two things merging through with interference. The interference which is lost, and in the same way the time spent by a particle is lost to interference between different scenarios. Makes no immediate sense to argue whether tunneling is instantaneous or a finite time. It's lost, it's gone. Sorry, this. Right, so one big question remains, what the amplitudes are doing in quantum theory. Nobody knows. Feynman said, don't ask. Oh, you'll get in trouble. Right.
So time to a few questions now. I know there are many people here who like weak value and who do not like weak value. Let us start with.
Thank you. It was a very interesting talk.
Thank you.
I'd just like to get a clarification. Are you being a Copenhagenist and saying that such questions are not allowed in the theory?
No, I'm a Feynmanist. No, I'm saying, I don't know. I think I'm saying no more than is said in the first 7 pages of Feynman's undergraduate text. So anything should be can be so related to that particular text. Quantum interference merges things together completely. Two ways. I could say it much simpler. If you have 2 double-slit experiments, you can't tell which way you go. I would interpret it like this. To you and to me, there are 2 holes. I drill them, and I look them through a microscope. But for an electron with a large wavelength, they're not. They're just one route leading from the source to the final stage, its final location on the screen. It doesn't. Interference through this merges 2 holes into what is 2 holes to us. It is just one route to it. That's my.
Yeah, but that's one way of looking at it. If you believe in the Bohmian philosophy, then you can actually think of paths.
Yes, and you can get Bohmian times, and people have done that.
That's right. That's why I was
the trouble is if you do that, you get a number, put you in the pocket, and go home. But if you try to do anything with that number, if you try to predict any, well, you say, okay, Bohmian says my electron from the wave packet comes from the first part of the wave packet and is spent on average this time there. So you have nice, real, positive time, not exceeding anything. But if you try to use this time to describe any experiment, you're in trouble because Bohmian is very clever in this sense. But it's only for electron on its own. Which, if you probe it, then you bring in the equipment, and then you have to Bohmian theory for this thing and equipment, and that would bend your trajectories. So it gives you moral satisfaction this time, as it did to, I think, Rick Levins was doing this for a long time.
But that was, I thought that was the advantage of the Bohmian theory. You didn't have to give up.
Well,
conventional.
if you're only prepared to be satisfied to a certain level, to
yes.
some moral, then it's perfect. But if you're trying to go further, then Bohm said, no, you can't, of course. If you want to know something which you can't check.
Okay. Secondly, I would just like to point out that when Nimtz was claiming superluminal tunneling.
Oh, Nimtz beamed, what was it?
Actually,
Mozart's system back in time.
We published a paper in Physical Review showing that there was actually, if you use Maxwell's theory correctly,
yes,
then you can show that there is actually no superluminal tunneling at all.
No.
It's consistent with relativity.
It's called reshaping. It's coming in the other. It comes from the first part of the wave, which is already there. So
advanced waves that come. So it's a very complicated.
It's already there. The shape is made, but the tail of the thing is already. Nothing happens if it. Yeah.
There are many questions I can see, but let's.
I might have misunderstood your talk. I'm not really clear on the specific question you're critical about regarding weak interaction and weak measurement, because there is this paper of Duck and Sudarshan which establishes a region of validity for weak value interaction amplification as such. Could you explain the specific question which you are critical about? I mean, there are many questions.
No, I'm not critical about any application. I'm critical about interpretation. I'm critical about saying this strange, outlandish things, getting them published in Nature, and making naive people think that quantum mechanics is something it isn't. Really. But no. What I'm saying, everything you can say about the amplification, everything is correct. Just don't think there's any physics which wasn't there, in final.
So you're probably aware of the experimental results claiming to have unprecedented precision.
Sorry, I can't hear you very well for some reason.
Hello?
Yeah.
Do you hear? Okay. So I guess you are aware of experimental results claiming to achieve unprecedented precision using weak measurements. So my first question is, do you think those papers have wrong statement in them?
Well, it depends on which papers you have in mind.
So let's say the Kvyat and Howell, you know, ultra sensitive and you know, spin Hall effect of light.
Oh, right. Hang on. Again, it's about are we talking about this tunneling time?
No. I'm talking about this like first papers claiming to have like amplification and like to improve precision using weak measurements.
No, no. I think the experimental results are correct.
Correct.
You could get them without using words weak measurements.
Yeah.
So you can do just the usual perturbation theory and be there.
Okay, but inspiring people to do new experiments and achieve a new result, wouldn't that be called as new physics?
It depends how you inspire people. I mean, if you there are limits of decency in inspiration.
I just am curious to know your understanding about, can the weak value be interpreted even in classical probability theory? How
No.
would you present a weak value in the classical probability theory?
No. There's a paper by, hang on, I think you're probably referring by Ferry, and there was a paper in 2014 by people from Albuquerque who claim, oh, it's quantum mechanics nothing. If you do this, and that in classical statistics, you get these extraordinary weak values. The answer is wrong. They're all people, including everybody wrote a comment on it. The reason is quite simple that you can't have it. Let me put it like this. I had a slide, but I probably don't have time to show it. If you have two positions, B1 and B2, and you have probabilities which are both non-negative, the average value will lie between B1 and B2.
Yes.
If, on the other hand, through some way, you let your probability change sign, this probability is positive, this is negative, all the bets are off. Because now the probability, well, the mean does not lie between the values. It can go to plus infinity, minus infinity. The variance can be anything. It can be zero. There's a famous, in 1987, Buzz was discussing collision time. And he claimed that collision time was sharply defined. It's the unique duration for elastic collision. But it's not true. What he evaluated the mean and the variance with distributions he did know was changing sign. And it's entirely possible to find a spread distribution which changes sign, which has zero variance. If the distribution was positive, that would force the distribution to be a delta function in sharp value. But if it's like that, it doesn't mean anything. So nothing like that. Classical statistics do not use negative probabilities for observable outcomes. Full stop. Can't be.
No, the question is something like, do you have some random variable whose expectation value would give you this weak value? In the sense that you have some observable,
Yes.
but not what is interpreted.
Absolutely. You measure something in purely normal quantum mechanical way. That turns out to link through theory but to certain amplitudes. So you can get the values of amplitude from perfectly something measured with probability. It's a sort of roundabout trick by the weak measurement people. You build amplitudes into the theory. And then you can everything you do then expressed in terms of amplitudes. And from your results, you can learn something about the amplitudes, and it's normal.
Yeah, right. Thanks. I have another point of the question on the tunneling time. You mentioned about this is the third option. That means it's the modular and the absolute value of this weak value of this tau. But that's the reason. Your reason is that's the only the positive number of the tunneling time. I agree with this point. But in that now is you assume that non-relativistic to the quantum mechanics. That's why it's needed. Why do we need it is that the choose of the tunneling time can be taken as that's the absolute value of that is that the tau of the weak value.
We don't need to choose. People have choose. I mean, they look at that various result and say which one is most. If there is a time, then probably the modulus is the likeliest candidate. But you can look at it has two properties you like. It's
right.
It's positive. It's not. It's real. But unfortunately, it fails in the third. It's not always shorter than the total expression of motion. It shows the general problem with weak values, with interpreting the weak values. You can say, I suggest, that the quantum particle can move for 3 seconds and spend an hour and a half somewhere else.
Yeah.
And that would be great because, and then you can say, oh, that's good for people because you can have 1 week of holidays, but you can spend 3 months in the sun before coming back to the office.
Right.
But if you were telling that to people, you'll be wrong. I mean, people won't be able to do that. So there's no. It just shows what would happen if you decide to choose the modulus.
Right.
It looks like better than the other 2 options, but it really isn't.
Yes. So that's the what is the I don't understand what is your opinion of this choosing on that's the tunneling time. What is the proper time?
There is no time.
Proper definition
Oh,
that's the tunneling time. What it is?
Oh, my opinion, there is no more time spent in the barrier than there's a number of slit, chosen by the particle in the double slit experiment. In a unique quantum way, those quantities are lost to interference. And if you try to get it through tingling your system weakly, you get something about the amplitudes. And you shouldn't trust, and you shouldn't interpret this information about the amplitude as a real-time interval, because then you're in trouble with, in a very spectacular way, spending an hour and a half while being in motion 3 seconds.
It's okay.
Okay, so let's think once more.
Yeah.